Hello there, and welcome. I am so glad you found your way here tonight. Whether you stumbled across this video on purpose, or it simply appeared at the right moment, I want you to know you are exactly where you need to be. Maybe it has been a long day. Maybe your mind is still working through the details of everything that happened, or turning over things left unsaid, plans left unfinished, worries that have no real shape yet but feel heavy anyway. That is all right. All of that can wait. None of it needs you right now. You have nothing to do tonight but rest. Tonight, we are going to drift together through one of the quietest, most extraordinary corners of the universe. Neutron stars. These are the remains of enormous suns that once blazed with light for millions of years, and then, in a single moment, collapsed into something so dense, so small, so unimaginably compressed, that the mind barely knows how to hold it. They are ancient and they are patient, and they spin in the dark in ways that science is still slowly learning to understand. We will take our time with them tonight. There is no rush. There is nowhere else to be. So let your body settle into wherever you are lying. Let your shoulders drop. Let your jaw unclench. Let your breath find its own slow rhythm. And if sleep comes before we finish, that is perfectly fine. That is the whole point. If these calm journeys through the cosmos help you unwind at the end of a long day, consider subscribing, one sleepy soul at a time. Now, let us begin. A neutron star packs more mass than our entire sun into a sphere the size of a city. Take a moment to let that settle. Our sun is so large that roughly 1 million Earths could fit inside it. And yet, when certain massive stars reach the end of their lives, all of that material collapses inward, not into a sprawling cloud, not into a gradual dimming, but into something roughly 10 to 15 miles across. The same amount of matter, pressed into something you could theoretically drive across in 20 minutes. The gravity at the surface of a neutron star is so intense that if you dropped a marshmallow from 1 meter above it, that marshmallow would hit the surface with the energy of an atomic bomb. This is not exaggeration. This is just physics, doing what physics does when matter is squeezed beyond what we usually allow ourselves to imagine. The numbers describe something that feels more like poetry than science, and yet it is real, quietly burning in the dark between the stars. Everything vast, it seems, can be compressed into something very still. A single teaspoon of neutron star material would weigh about 4 billion tons on Earth. Pause with that for a moment. A teaspoon. The kind you use to stir your tea, to measure vanilla extract, to feed a child medicine on a slow Sunday morning. If you could somehow scoop up that tiny volume of a neutron star and bring it here, it would immediately fall through the floor, through the Earth's crust, through the mantle, and settle somewhere near the planet's core. Nothing on Earth could hold it. No material we have ever made, no structure we have ever built, could bear that weight. It is a strange thought to sit with, that something so small in volume could carry such impossible density. We tend to think of heaviness as something big, something looming. But neutron stars remind us that the most profound things can be very, very small, quietly enormous, still and immovable, drifting through the galaxy in the dark. Density, we learn, is not always visible from the outside. Neutron stars are born in the violent death of a massive star. When a star, many times more massive than our sun, exhausts the last of its nuclear fuel, it can no longer support its own weight. For millions of years, the outward push of nuclear fusion has held gravity at bay, a constant, slow negotiation between two enormous forces. But when the fuel runs out, that negotiation ends. The core collapses in less than a second. The outer layers rebound off this impossibly dense core and explode outward in what we call a supernova, one of the brightest events in the known universe. And left behind, in the quiet center of all that wreckage, is the neutron star. Small, dense, still spinning, radiating heat. It is as if the universe reaches a kind of threshold and decides, in a fraction of a second, to begin something entirely new, something patient and old and very, very dense. What is left after the storm is often the most enduring thing. Neutron stars spin faster than almost anything else in the known universe. When the original massive star collapses, it carries its rotation with it, and as the core shrinks, that rotation speeds up, the same way a figure skater pulls in her arms and begins to spin faster. A star that once rotated slowly over many days can collapse into a neutron star that completes hundreds of full rotations every single second. The fastest known neutron stars, called millisecond pulsars, spin more than 700 times per second. Try to imagine that. Something roughly the size of Chicago, spinning over 700 times in the time it takes you to blink. And yet these objects do not fly apart. Their gravity is so immense that even at those rotational speeds, the surface holds together. Everything about neutron stars seems to operate at the very edge of what matter is allowed to do. Speed and stillness, in the cosmos, often live side by side. The surface of a neutron star is covered in a crust made of iron nuclei, arranged in a perfect crystal lattice. Most objects we think of as having a surface, a planet, a moon, a rocky asteroid, have that surface shaped by geological processes, erosion, weather, impact. The surface of a neutron star is different. It is a crystalline lattice of atomic nuclei, arranged with a precision that no earthly crystal can match, because the gravity pressing down on it is so extreme that even the slightest imperfection would immediately be smoothed away. This crust is extraordinarily rigid. It is thought to be 10 billion times stronger than steel, and yet sometimes that crust does crack, in what astronomers call a starquake. A tiny fracture in something 10 billion times stronger than steel, releasing more energy in a fraction of a second than our sun puts out in years. The universe occasionally reminds us, quietly, that even the most rigid things eventually shift. Even the hardest surfaces, given enough time, find a way to breathe. Neutron stars have magnetic fields trillions of times stronger than anything we can produce on Earth. Earth has a magnetic field. It is what makes compasses work, what guides birds on their migrations, what gently deflects the solar wind. It is a subtle, invisible presence in our lives, something most of us never think about. The magnetic field of a neutron star is something else entirely. It can be 1 trillion times more powerful than Earth's. These extreme magnetic fields shape the radiation that pours off the star, bend the paths of charged particles, and in some cases create objects called magnetars, a special class of neutron star with fields so intense that if one were to pass within a few thousand miles of Earth, it would erase every credit card and disrupt the iron in your blood from that distance. They exist in the galaxy, quietly, far away. Their fields hum across the dark with a patience that predates us entirely. Ancient forces work quietly in places we will never visit. Pulsars are neutron stars that sweep beams of radio waves across the galaxy like cosmic lighthouses. As a neutron star spins, its powerful magnetic field funnels radiation outward from its magnetic poles. If those poles are tilted relative to the spin axis, which they often are, then the beams sweep around like the beam of a lighthouse sweeping across a harbor. If Earth happens to be in the path of that sweep, we receive a pulse of radio waves with every rotation. Regular, precise, repeating. When the first pulsar was discovered in 1967, the signal was so regular that some astronomers briefly wondered whether they had detected a signal from an intelligent civilization. They even gave it the informal nickname LGM-1, Little Green Men. Of course, it turned out to be something far more quiet than that. A dead star, spinning in the dark, doing what physics told it to do, sending its patient signal out into a universe that eventually learned how to listen. Something has been sending its signal outward long before anyone was listening. Some neutron stars will spin for billions of years without slowing down noticeably. Friction, in space, is almost nothing. There is no atmosphere to push against, no ground to drag on, no medium to resist the rotation. And so a neutron star, once set spinning by its birth, continues spinning for timescales that are difficult to hold in the mind. Millisecond pulsars, the fastest spinners, are thought to have been spun up by stealing material from a companion star, and they may maintain their extraordinary rotation rates for longer than the current age of the universe. The universe is roughly 13.8 billion years old. Some of these stars may spin steadily for many times that span, quietly, in the dark, long after every planet we have ever named has been consumed or cooled or drifted away. There is something both lonesome and deeply peaceful about that image, a patient, spinning light in a universe that has grown very old around it. Even now, as you drift, there are stars out there simply turning, turning and turning, in the patient dark. The density inside a neutron star pushes the very concept of matter to its limits. We are used to thinking of matter as made of atoms, a nucleus in the center, electrons orbiting around it, and mostly empty space in between. Atoms are, famously, almost entirely empty. But inside a neutron star, that emptiness has been squeezed out entirely. The electrons have been forced into the protons, forming neutrons. The neutrons are pressed together so tightly that they essentially touch. In the deepest layers, the pressure may be high enough that even neutrons begin to dissolve into their constituent quarks. This region, if it exists, would be a quark-gluon plasma, a state of matter that has not existed freely in the universe since fractions of a second after the Big Bang. We are not entirely sure what lives at the center of a neutron star. The physics becomes, in the gentlest sense, unclear. That uncertainty is not a failure of science. It is simply the universe keeping one of its quieter secrets. Some rooms in the cosmos are kept dark, and perhaps that is as it should be. Neutron stars cool very slowly, over millions of years after their formation. At birth, a neutron star is extraordinarily hot, perhaps 100 billion degrees in its interior, in the first moments after formation. It radiates energy rapidly in the beginning, mostly through particles called neutrinos, that stream outward through the star and carry heat with them at nearly the speed of light. This cooling phase lasts for thousands of years. After that initial rush of cooling, the process slows dramatically. A neutron star 1,000,000 years old may still have a surface temperature of around 1,000,000 degrees, far hotter than the surface of our sun, and yet so small and so far away that most of them are invisible to the naked eye, glowing only in X-rays. Slowly, across timescales that dwarf anything in human history, they cool, they dim, they grow still. They carry their heat like a memory, radiating it patiently into the space around them, degree by degree, across millions of quiet years. Warmth, given enough time, always finds its way outward. Neutron stars were theorized in 1934, just 2 years after the neutron itself was discovered. In 1932, physicist James Chadwick discovered the neutron, the neutral particle that lives in atomic nuclei, alongside protons. 2 years later, in 1934, Walter Baade and Fritz Zwicky proposed something remarkable. They suggested that when a massive star dies in a supernova, the core might collapse into a star made entirely of neutrons, packed together like a solid ball of nuclear material. They wrote this up as a brief note in a scientific paper, almost as an afterthought at the end of a broader discussion. At the time, it seemed so extreme as to be nearly science fiction. There was no way to detect such an object. There was no evidence one had ever existed. They were simply following the physics to its logical conclusion, the way a quiet river follows its own slope downhill. 33 years later, the first pulsar was discovered, and Baade and Zwicky were proven right. Some ideas arrive long before the instruments exist to confirm them. The collapse that creates a neutron star happens in less than 1 second. It is worth pausing on this. A star that has been burning for 10 million years, sustaining itself through the slow, quiet fusion of hydrogen, helium, carbon, oxygen, neon, and silicon, collapses in under a second. The outer core falls inward at a quarter of the speed of light. The entire event, the collapse and the rebound, takes less time than it takes you to complete one breath, and in that fraction of a second, more energy is released than our sun will emit across its entire 10 billion year life. Almost all of that energy leaves as neutrinos, particles so small and so weakly interacting that they pass through the Earth like it is not there. A supernova on the other side of the galaxy would flood the Earth with neutrinos, and we would never feel them. The cosmos, even in its most violent moments, moves through us without a sound. The most transformative moments in the universe arrive without a warning and leave without a trace. Neutron stars are so dense that space itself is measurably curved around them. This is not a metaphor. Einstein's general theory of relativity tells us that mass warps the fabric of space-time. The more mass, the more warping. Near a neutron star, this effect is dramatic enough to actually bend light. If you were somehow able to float above a neutron star and look outward, you would see the stars behind you reflected back to you from the star's surface below, because light bends so sharply around the star that it can travel from behind you, wrap around, and reach your eyes from the direction of the star itself. In fact, you could see more than half of the star's surface at once, because the curvature of space acts like a curved mirror, folding light around the object. The universe, near a neutron star, does not behave the way our everyday intuition expects. Space becomes something you can feel. Gravity, near these quiet objects, is not a force so much as a shape in the dark. Some neutron stars are found in binary systems, orbiting another star in a slow, patient dance. Many stars in the galaxy do not travel alone. They form in pairs, bound to each other by gravity, circling one another across timescales that outlast whole civilizations. When one of those stars is massive enough to end its life as a neutron star, the surviving pair becomes something extraordinary, a dense, spinning remnant in close orbit with a living star, sometimes close enough to pull material off its companion. This material falls toward the neutron star in a swirling disk called an accretion disk, growing hotter and hotter as it spirals inward, until it glows in X-rays. These systems, called X-ray binaries, are some of the brightest X-ray sources in the sky. Two objects in an ancient, quiet partnership, one giving, one receiving, circling each other in the dark, with a patience that has lasted millions of years. Some partnerships in the universe are built on gravity alone, and they last longer than anything else we know. Magnetars are the most magnetically extreme objects ever discovered in the universe. All neutron stars have powerful magnetic fields, but magnetars take this to an entirely different level. Their fields are roughly 1,000 times stronger than those of ordinary neutron stars, which are themselves already 1,000,000,000,000 times stronger than Earth's field. A magnetar's magnetic field is so intense that it distorts the very shapes of atoms. Electrons near a magnetar are forced into elongated, pencil-thin orbitals rather than their usual spherical distributions, because the magnetic force overwhelms the atomic forces that normally determine their shape. Magnetars flare suddenly and unpredictably, releasing enormous bursts of gamma rays and X-rays in fractions of a second. In 2004, a magnetar on the other side of the Milky Way released a burst of energy that, despite the distance of roughly 50,000 light-years, was detectable on Earth, with instruments already pushed to the edge of their sensitivity. It ionized the upper atmosphere briefly, like a distant whisper that still managed to rattle the windows. Out there, something ancient and still occasionally makes itself known. Neutron stars can slowly capture material from a companion star and reignite as X-ray bursters. When a neutron star in a binary system draws material from its companion, that material, mostly hydrogen and helium, accumulates on the surface, The surface of a neutron star is already extraordinarily hot, and as the layer grows thicker, the temperature and pressure at the bottom of that accumulating pile become enormous. Eventually, the hydrogen ignites in a thermonuclear burst, not a controlled, slow fusion like what happens inside a living star, but a sudden, violent flash that spreads across the entire surface in seconds. For a brief moment, the neutron star blazes with the brightness of roughly 100,000 suns. Then it quiets. The material is gone, and slowly, over hours or days, the accumulation begins again. Patient, inevitable, the same process repeating, over and over, across millions of years, in the dark places between the stars. The universe, it turns out, has a very long memory for repetition. Neutron stars are threaded with superfluids that flow without resistance deep inside their cores. Superfluidity is a state of matter that occurs at extremely low temperatures here on Earth. Liquid helium, cooled near absolute zero, becomes a superfluid that can flow up the walls of a container, escaping without friction. Inside a neutron star, something similar happens, but not because of low temperature. The neutrons in the inner layers of the star form what physicists call a neutron superfluid, a quantum state in which the neutrons flow without any resistance whatsoever. This superfluid is thought to rotate independently of the solid crust, and when the two fall out of sync, the star can experience what astronomers call a glitch, a sudden, tiny speed-up in rotation, as the superfluid transfers some of its angular momentum to the crust. These glitches are small, but they are measurable. They are the neutron star's interior, making itself known from the outside, a deep, quiet shift that travels up through layers of impossibly dense matter and reveals itself as a fraction of a second's change in the pulse. What moves deep inside a thing will always, eventually, find its way to the surface. Tonight, while you breathe slowly, somewhere in the galaxy, a neutron star is glitching, speeding up by the smallest fraction, then settling back into its patient rhythm, as if adjusting itself for the long journey ahead. The light from a neutron star's surface is shifted toward the red end of the spectrum by gravity itself. This is called gravitational redshift, and it is one of the predictions of general relativity confirmed by observation. When light climbs out of a deep gravitational well, and the gravitational well of a neutron star is about as deep as anything outside a black hole, it loses energy in the process. Losing energy means its frequency drops, and lower frequency means redder light. By measuring precisely how much the light from a neutron star's surface is redshifted compared to what we expect from its temperature, physicists can actually calculate the ratio of the star's mass to its radius. They can learn about the structure of the interior, how stiff or how soft the matter is, simply by watching the color of the light that escapes. Gravity leaves its fingerprint on the light it allows to leave. The universe writes its own measurements into every photon it releases. Every color of light that reaches us carries a memory of where it has been. The first binary pulsar discovered earned its discoverers the Nobel Prize in Physics. In 1974, astronomers Russell Hulse and Joseph Taylor discovered something remarkable: a pulsar in orbit with another neutron star. Two neutron stars circling each other at high speed, their mutual gravity bending space around them in waves. Einstein's general relativity predicted that two massive objects in close orbit should radiate energy as gravitational waves, ripples in the fabric of space-time, and slowly spiral together as that energy is carried away. Hulse and Taylor measured the orbital decay of this system over years. The rate at which it was spiraling inward matched Einstein's predictions to extraordinary precision. This was the first indirect evidence that gravitational waves exist. They shared the Nobel Prize in Physics in 1993. The two neutron stars, meanwhile, continue their slow inward spiral, unaware that human beings on a small planet spent decades watching them, taking notes in the quiet. We have learned many of our deepest truths by watching patient things that do not know they are being watched. Neutron stars emit X-rays that can be detected by space-based telescopes orbiting Earth. Our atmosphere is, in many ways, a remarkable shield. It protects us from the worst of the radiation that streams in from space, absorbing X-rays and gamma rays before they reach the ground. This is a good thing for living creatures. It is a difficulty for astronomers, who cannot study X-ray emitting objects from the ground, and so we have sent telescopes into orbit. Instruments, like the Chandra X-ray Observatory, which has been watching the X-ray sky since 1999, and the Newton telescope, operated by the European Space Agency. These instruments have given us detailed portraits of neutron stars, binary systems, supernova remnants, and magnetar flares from far across the galaxy. They orbit the Earth in the quiet above our atmosphere, turning slowly, pointing their mirrors toward the sky, with a patience that mirrors the objects they study. We had to leave the ground to hear what the sky was saying. The matter inside a neutron star is sometimes called nuclear pasta because it forms layered, twisted shapes under extreme pressure. This is one of those corners of physics where the language tries its best and falls a little short. In the deepest layers of a neutron star's crust, the nuclei of atoms, which normally sit discreetly apart from one another, begin to merge and deform under the crushing pressure. They form sheets, tubes, and bubbles. Physicists, in a charming moment of informality, named these shapes after food: gnocchi, spaghetti, lasagna, anti-spaghetti, Swiss cheese. The nuclear pasta phase is thought to be the strongest material in the known universe, stronger, per unit area, than anything else we have theorized, and it exists in a place we can never reach, at densities we can never create, in the core of an object no larger than a city, drifting in the ancient dark between the stars. The universe builds its strongest things in its most inaccessible places. The deepest structures are always hidden from view, held in the quiet dark. Neutron stars were first directly observed as pulsars by a graduate student named Jocelyn Bell Burnell in 1967. In the summer of 1967, a young graduate student at Cambridge University was working with a radio telescope that she had helped to build, a sprawling array of antennas covering nearly 4 acres of English countryside. Her job was to analyze the reams of paper chart recordings that the telescope produced. It was patient, meticulous work. And one day, she noticed something unusual, a signal that pulsed with extraordinary regularity, appearing 4 times a day as the Earth's rotation brought it into the telescope's view. She investigated, she measured, she confirmed. She had discovered the first pulsar. Her supervisor received the Nobel Prize. She did not. She has since received almost every other honor the scientific community can offer, and she has spoken about the experience with a grace and patience that mirrors the objects she first found. The universe, sometimes, asks more of some people than others. Quiet work, done with care, can change what we know about the sky. Some neutron stars have surfaces hot enough to glow faintly in visible light, though we have only detected a handful this way. Most neutron stars reveal themselves through radio waves, X-rays, or gamma rays. But a very small number, only about 7 are confirmed, are hot enough and close enough to Earth that they emit faintly in the optical range. These are called the Magnificent Seven in the astronomy community, a quiet nickname for 7 objects that are more dense than imagination and more distant than driving, but faintly visible to sensitive enough instruments in the wavelengths of light that happen to fall within the range of human vision. They do not look like stars. They are not bright enough to see with any backyard telescope, but they are there, glowing dimly in the dark, cooling slowly, each one a city-sized remnant of something that burned for millions of years and then chose a different kind of existence. Even dying things keep a quiet glow, long after the brightest part is over. The Crab Nebula, at the center of a famous cloud of glowing gas, is a neutron star spinning 30 times per second. In 1054, Chinese and Arab astronomers recorded a new star in the sky. one bright enough to see in daylight for weeks. What they were witnessing was a supernova, the death of a massive star some 6,000 light-years away. The explosion sent material outward in a glowing, expanding cloud that we can still see today through any small telescope, a tangled, glowing rows of gas and filaments known as the Crab Nebula. And at its center, spinning 30 times every second, is the neutron star born in that explosion. It powers the entire nebula. Its spinning magnetic field generates a wind of particles that fills the surrounding gas with energy and keeps it glowing. The Crab pulsar has been spinning and radiating for nearly 1,000 years, and it was already ancient news to the universe before any human being wrote it down. Some things have been burning quietly for centuries before anyone thought to name them. Neutron stars occasionally collide with one another, and those collisions forge heavy elements including gold. For a long time, astronomers puzzled over where the heaviest elements came from. We understood that hydrogen and helium were made in the Big Bang, and that elements up to iron were forged in the cores of stars. But gold, platinum, uranium, elements heavier than iron, could not be made in ordinary stellar fusion. They required something more extreme. In 2017, two neutron stars spiraling together from the 1974 discovery were not the ones observed. A different pair was caught in the act of merging, detected simultaneously by gravitational wave detectors and by telescopes around the world. The event, called a kilonova, produced light and gravitational waves, and, in the aftermath, an enormous quantity of heavy elements: gold, platinum, strontium. The gold in your wedding ring, if you wear one, was almost certainly forged in the collision of two dead stars, somewhere in the ancient galaxy, long before our solar system existed. The gold we wear quietly carries the memory of something that ended so we could begin. Gravitational waves from merging neutron stars were first detected in August 2017. The detection came through an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory, along with its European partner, Virgo. These instruments measure gravitational waves by splitting a laser beam and sending each half down a long tunnel, then recombining them and looking for tiny differences in the time each beam takes to travel. Tiny differences caused by the stretching and squeezing of space itself as a gravitational wave passes through. In August 2017, both instruments detected a signal, a chirp in the fabric of space-time from two neutron stars spiraling together and colliding roughly 130 million light-years away. Telescopes around the world swung to look at the location. They found the kilonova. They found the heavy elements. They confirmed what Einstein had predicted, what Hulse and Taylor had inferred, what decades of patient science had slowly built toward. The universe had been sending that signal for 130 million years, and we finally had the instruments to receive it. Every signal, no matter how ancient, eventually finds a listener. Millisecond pulsars are so regular that they rival atomic clocks in precision. An atomic clock keeps time by counting the oscillations of a cesium atom. It loses about 1 second every 300 million years. Millisecond pulsars, spinning hundreds of times per second with extraordinary rotational stability, can match or exceed this precision over short timescales. Astronomers have proposed using arrays of millisecond pulsars, called pulsar timing arrays, as detectors for very low-frequency gravitational waves. The idea is that gravitational waves passing through the galaxy would cause tiny variations in the arrival times of pulses from pulsars in different directions. By monitoring many pulsars simultaneously over years, you could in principle detect waves far too long and slow to be picked up by LIGO. This technique has recently produced early results suggesting the detection of a gravitational wave background, a slow rumble in space-time itself, likely produced by pairs of supermassive black holes in the distant universe. The universe uses dead stars to measure its own vibrations. The oldest clocks in the universe keep their time without being asked. Neutron stars have an escape velocity close to half the speed of light. Escape velocity is the speed you need to reach to break free from an object's gravitational pull. For Earth, it is about 11 kilometers per second, manageable, in principle, for a rocket. For our Sun, it is about 600 kilometers per second, enormous by human standards, but still far below the speed of light. For a neutron star, the escape velocity is roughly half the speed of light, roughly 150,000 kilometers per second. Nothing we have ever built could approach that speed. Light itself can escape a neutron star, barely, but it leaves slower and redder than it arrived, having spent enormous energy climbing out of the gravitational well. Anything slower than half the speed of light that reached the surface of a neutron star would be trapped there forever, pulled down into the crystal crust and lost. The universe has gravity wells that make escape feel, even for light, like a long, slow climb. Some places in the cosmos hold on to things very quietly, and for a very long time. A neutron star's radius is almost exactly predicted by quantum mechanics. This is one of those moments where two branches of physics, general relativity, which governs the large, and quantum mechanics, which governs the small, are forced to confront each other directly. The radius of a neutron star depends on how stiff or soft the matter inside it is, what physicists call the equation of state. And the equation of state depends on the quantum mechanical behavior of densely packed neutrons and possibly quarks. Measurements from the NICER telescope, which is mounted on the International Space Station and measures X-rays from neutron star surfaces with extraordinary precision, have given us the most accurate measurements of neutron star masses and radii to date. They show that neutron stars are roughly 10 to 14 kilometers across, which is consistent with theoretical predictions. The universe, in this quiet way, confirms that the mathematics we wrote down in small rooms on Earth actually describes the behavior of the densest matter in existence. The equations we write in quiet rooms turn out to describe the loudest places in the universe. Some neutron stars are completely invisible. They emit no detectable radiation and are found only through their gravitational effects. We can detect most neutron stars because they emit something: radio waves, X-rays, gamma rays, visible light, but not all of them. Some have cooled enough that they no longer emit significant radiation in any band we can measure. Some have magnetic fields that have decayed so much that they no longer produce the lighthouse beams of a pulsar. These are called dark neutron stars, or sometimes, more poetically, dead pulsars. We know they must exist in enormous numbers because we can estimate how many supernovae have occurred in the history of the galaxy, and the number of detected neutron stars is only a small fraction of that. Most of them are simply dark, silent, drifting through the spiral arms of the Milky Way without announcing themselves, invisible to our instruments, patient in a way that even the universe seems reluctant to disturb. Quietly, the cosmos moves around you, and most of what it carries in silence. Some neutron stars appear to be isolated, showing no signs of a binary companion or surrounding nebula, and yet they pulse with faint thermal radiation, suggesting they are young and warm. These are called the Magnificent Seven, a group of nearby, slowly cooling X-ray emitters that stand apart from pulsars, magnetars, and X-ray binaries. They drift alone through the galaxy's thin gas, not pulling material from a companion, not sweeping a lighthouse beam across the sky. They simply glow. Warm, dense, silent. They are thought to be relatively young, 1,000,000 years old or less, still radiating the heat of their birth. Astronomers study them to learn about the cooling processes of neutron star interiors, using their surface temperatures as windows into the physics of the deepest layers. They are some of the most isolated objects in the galaxy, and yet they are illuminating, quietly present, quietly warm, resting in the dark between the stars. Something still warm can rest quietly in a very cold place. The International Space Station hosts a telescope dedicated entirely to studying neutron stars. It is called NICER, the Neutron Star Interior Composition Explorer, and it was installed on the station in 2017. From its vantage point in low Earth orbit, NICER watches X-ray pulses from neutron stars with extraordinary timing precision, recording the arrival times of individual X-ray photons to within nanoseconds. By studying how those pulses vary as the hot spots on a neutron star's surface rotate in and out of view, scientists can map the surface geometry and derive the mass and radius of the star. It is a remarkable piece of science, happening very close to home. While most of us sleep, the International Space Station circles the Earth once every 90 minutes, and aboard it, a quiet instrument watches the faint flickering of dead stars and sends its measurements down to researchers working through the night at their computers. Above us, the sky is always being watched. Even now, as you drift, something above you is quietly listening to the pulse of dead stars. Neutron stars are expected to eventually become black holes if they accrete enough mass. There is a limit to how much mass a neutron star can hold. Beyond a certain threshold, thought to be roughly 2 to 3 times the mass of our Sun, the quantum pressure of the neutrons can no longer resist gravity. The star collapses further. Past that threshold, nothing can stop the collapse. What was a neutron star becomes something with no surface, no size, no escape, a black hole. This transition can happen in a neutron star binary, when the star pulls enough material from its companion to push itself over the limit. It is not explosive, or at least not necessarily so. The star simply crosses a threshold and becomes something else, something that cannot be seen, something that can only be inferred from the behavior of the space around it. The neutron star does not resist. It simply reaches the end of what it is allowed to be and becomes something quieter still. Every threshold, crossed quietly enough, becomes a new kind of beginning. The radio pulses from some pulsars are so precise that they were initially mistaken for artificial signals. There is a particular quality to the radio pulses from millisecond pulsars. They arrive with clockwork regularity, sharp and distinct, repeating without variation. When Jocelyn Bell Burnell first noticed them, the signal was so precisely periodic that she and her colleagues briefly entertained the possibility that it was something artificial. Not a satellite, not interference, something intelligent. She marked the data with the half-joking notation, LGM1, little green men. Of course, what she had found was not an artificial signal. It was a natural one, but natural processes that produce precision approaching that of a manufactured clock are so rare that the confusion was understandable. The universe, in this case, had produced something that looked, for just a moment, like a message. It turned out to be the first detected remnant of a dead star, pulsing with a patience and regularity that needed no sender and no receiver. It simply was. Some things in the universe are so orderly, they look, at first, like they were meant for us. Neutron stars produce the most powerful natural explosions currently known, called soft gamma repeater giant flares. Magnetars, those extreme neutron stars with the most powerful magnetic fields, occasionally release bursts of energy that are, in every measurable sense, the most powerful explosions currently known in the universe, short of gamma-ray bursts. In December 2004, a magnetar designated SGR 1806-20, located about 50,000 light-years away on the other side of the galaxy, released a burst of energy in 0.2 of a second that exceeded the total energy output of our Sun in 250,000 years. In 0.2 of a second, the burst was so intense that it measurably ionized Earth's upper atmosphere across the night side of the planet. And yet, because the magnetar was 50,000 light-years away, we are here to note it. The universe is generous with its distances. Most of its most violent events happen very, very far from the small, warm places where life has taken hold. Distance is one of the cosmos's quietest forms of mercy. Neutron stars, spin down very gradually, and by measuring that slowdown, astronomers can calculate a pulsar's age. Nothing in space spins forever at the same rate. Even in the vacuum between the stars, a pulsar loses energy slowly through the electromagnetic radiation it emits. Every beam of radio waves that a pulsar sends out carries away a tiny fraction of the star's rotational energy. Over millions of years, this adds up. The star slows, gradually, measurably. By comparing a pulsar's current spin rate to its rate of slowdown, which is also measurable, astronomers can calculate the characteristic age of the pulsar, an estimate of how long it has been spinning since it was born. This is not a perfect clock. It makes assumptions about the initial spin rate. But it gives a rough age, and for many pulsars, it matches well with other evidence, such as the age of the supernova remnant. The pulsar still sits inside. Dead stars, it turns out, carry their own age, written in their turning. Time writes itself into the spin of things that have been turning long enough to slow. The space around a rapidly spinning neutron star is dragged along with its rotation in an effect called frame dragging. Einstein's general relativity predicts not just that mass curves spacetime, but that a rotating mass drags spacetime around with it, the way a thick liquid is dragged around a spinning ball. This effect, called frame dragging or the Lense-Thirring effect, is tiny near Earth. It has been measured by the Gravity Probe B satellite, but the numbers are minuscule. Near a rapidly spinning neutron star, the effect is substantial. Space itself is being dragged around in the direction of the star's rotation. A gyroscope in orbit around a spinning neutron star would precess. It would slowly shift its pointing direction, at a rate caused entirely by the rotation of spacetime around the star. This is gravity not just pulling things in, but stirring the space around them. The universe, near a neutron star, is not simply curved. It is gently, persistently turning, like water around a slow drain. Even the fabric of space, near these dark objects, is set slowly turning. Some neutron stars are paired with white dwarfs and can accumulate material until they trigger thermonuclear runaway events called classical novae. When a neutron star orbits close enough to a white dwarf, or in some cases a larger companion star, it can draw a thin, steady stream of hydrogen-rich material from its partner. This material spirals down onto the neutron star's surface in an accretion disk, gradually building into a thin shell of hydrogen over time. When the temperature and pressure at the base of that shell reach a critical point, the hydrogen ignites in a runaway thermonuclear reaction that spreads across the entire surface in seconds. From Earth, this appears as a sudden brightening, a nova. The neutron star blazes briefly as the material burns away, then quiets again. And slowly, patiently, the accumulation begins once more. These events repeat on timescales of months to decades, depending on how quickly material builds up. The same star, the same process, the same patience, repeating in the quiet dark for millions of years. Some things in the universe are defined entirely by their willingness to repeat. Rest here for a moment. There is more to come. The light from distant neutron stars has traveled longer than the Earth has existed. When we point our telescopes at a neutron star 100,000 light-years away, the light arriving at our instruments left its source before our planet had formed, before the solar system had condensed from its cloud of gas and dust, before the sun had ignited. That light has been traveling through the cold dark of intergalactic and interstellar space for 100,000 years, passing through nothing, touching nothing, carrying its information faithfully across an abyss. And then it arrives here. It falls into our mirrors and our detectors, and we say, there is a neutron star, there. What we are seeing is not what is there now. It is a memory of what was there then. Astronomy, in this way, is always an act of reading the past. Every image we have ever taken of a neutron star is a portrait of something that has already moved on, cooled a little more, shifted by some tiny margin. We see what was. The universe shows us its diary, not its present tense. Every light that reaches us is already ancient by the time it arrives. Some neutron stars generate jets of particles that shoot outward at nearly the speed of light. When material falls onto a neutron star in a binary system, not all of it lands on the surface. Some of it is flung outward along the magnetic poles in narrow, focused streams, jets of plasma moving at a significant fraction of the speed of light. These jets extend for light years in some cases, leaving glowing trails of radio emission that trail behind the neutron star like the wake of a very slow boat in a very deep sea. The mechanism that produces these jets is still not completely understood. The interplay between the magnetic field, the infalling material, and the rotation of the star creates conditions that launch matter outward rather than inward. And the physics of this transition from accretion to ejection is one of the active frontiers of astrophysics. The neutron star, in these moments, is not just consuming, it is also releasing, sending a part of what it receives back out into the galaxy, contributing to the slow circulation of matter through space. What takes in and releases in equal measure becomes part of something larger than itself. The sound equivalent of a neutron star's vibration would be the deepest note imaginable. This is a thought experiment, not a physical reality. Sound cannot travel through the vacuum of space. But physicists have calculated what the oscillations of a neutron star would correspond to if translated into sound waves. When a neutron star rings after a glitch or a starquake, oscillating in its shape or its rotation, those vibrations have frequencies that correspond, in the language of music, to notes far below the lowest note on any instrument ever built. The deepest note on a bass guitar is around 41 Hz. The deepest note a pipe organ can produce is around 16 Hz, below the threshold of human hearing. The oscillations of a neutron star, translated into sound, would sit orders of magnitude below that, a vibration so slow and deep that no ear could ever detect it, but so powerful that if it were sound, it would shake apart everything nearby. The universe plays notes we can never hear. The deepest music in the cosmos is felt rather than heard, ancient and slow, and far below our range. Neutron stars have a photosphere, a thin outer layer where their radiation originates, just as the sun does. We think of the sun as having a surface, though it is not a solid surface. It is the layer of gas where the sun becomes opaque to outward radiation, the layer from which light finally escapes. This layer is called the photosphere. Neutron stars have one too, though it is extraordinarily thin by any standard, perhaps a meter or less in thickness, and sits above a surface of crystalline nuclear material. The properties of this photosphere are determined by the extreme gravity and intense magnetic field of the star beneath it. Studying the spectrum of radiation that emerges from this photosphere, its specific wavelengths, its precise temperature distribution, gives physicists a window into what lies below. The photosphere of a neutron star is so thin it barely exists, and yet it is the only part of the star that ever communicates with the rest of the universe. Everything else stays inside. The thinnest layer is sometimes the only one that speaks. Some neutron stars rotate so fast that their equatorial surfaces approach a significant fraction of the speed of light. For the fastest spinning millisecond pulsars, rotating at over 700 times per second, the equator of the star is moving at roughly 15% of the speed of light. At those speeds, the effects of special relativity become meaningful. Time on the equatorial surface ticks slightly differently than time at the poles. The shape of the star is distorted. Gravity and centrifugal forces compete, flattening the star at the poles and bulging it at the equator. The star is not a perfect sphere. It is an oblate thing, spinning impossibly fast, its equatorial material held in place only by the same extreme gravity that makes the star what it is. If it spun any faster, and some physicists calculate the upper limit to be around 1,500 rotations per second, the centrifugal force at the equator would begin to overcome gravity, and the star would tear itself apart. but the fastest known pulsars remain just below that limit. Stable, quiet, turning. As you rest tonight, somewhere a dead star turns faster than our minds can follow and does not come apart. The gravitational field of a neutron star would stretch a human body into a thin strand of matter in an instant. Tidal forces, the difference in gravitational pull between the side of an object closer to a massive body and the side farther away, are what stretch things apart near extreme gravitational sources. Near Earth, tidal forces are gentle enough that we feel them only as the slight stretching of the ocean into tides. Near a black hole, the concept of being stretched by tidal forces has the informal name of spaghettification. Near a neutron star, the effect is only slightly less extreme. If a human being were somehow transported to within a few hundred kilometers of a neutron star's surface, the tidal force, the difference in gravity between the head and the feet, would be enough to pull the body apart in fractions of a second. Not with violence or drama, but with complete and quiet certainty. The universe is not scaled for us. We exist in a very particular range of conditions, and the places where those conditions end are places we will never go. We are made for the gentlest corners of the cosmos, and that, perhaps, is its own kind of grace. The pulsar in the Vela supernova remnant is one of the closest neutron stars to Earth, about 1,000 light-years away. Vela is a constellation visible from the southern hemisphere, and within it, spread across a wide patch of sky, is the glowing remnant of a supernova that exploded roughly 11,000 years ago. At its center, the Vela pulsar spins about 11 times per second, slower than the Crab pulsar, older, further along in its gradual winding down. At roughly 1,000 light-years away, it is one of our nearest neutron star neighbors. 11,000 years ago, when that star exploded, human beings were just beginning to settle into the earliest permanent communities on Earth. Agriculture was new. Writing had not been invented. People looked up at the sky and saw a new star appear, blazing far brighter than anything around it, before fading over weeks. They could not have known what they were seeing. Now we know. And what we know is that the star left behind a patient, spinning remnant that has been turning in the dark ever since. Some things that ancient people saw in the sky are still there, still turning, still waiting to be understood. Neutron stars are expected to outnumber black holes in our galaxy. Black holes form from the most massive stars, those with perhaps 20 or more times the mass of our Sun. Neutron stars form from a slightly less extreme range of masses, stars roughly 8 to 20 times the mass of the Sun. Because less extreme masses are more common than very extreme ones, there should be more neutron star-forming events throughout the history of the galaxy than black hole-forming ones. Estimates suggest the Milky Way may contain as many as 1 billion neutron stars, though we have detected only a few thousand. Most of them are dark, cooled, quiet, no longer emitting in any wavelength we can detect. They drift through the spiral arms of the galaxy in vast numbers, patient and invisible, sharing the space between the stars with clouds of gas and dust and the slow migration of ordinary worlds. We are surrounded by them, in the statistical sense, though none is close enough to matter. The galaxy is quieter than it looks, and much more crowded than it seems. A neutron star's interior may contain a phase of matter called color superconductivity. Deep inside a neutron star, if the pressure is high enough to dissolve neutrons into their component quarks, something strange may happen. Quarks, which carry a property called color charge, the quantum equivalent of electric charge for the strong nuclear force, can form pairs, similar to how electrons pair in a superconductor. These quark pairs would form a state called color superconductivity, in which the strong force's equivalent of electrical resistance drops to zero. This is theoretical. We cannot build an experiment that reaches the pressures and densities required to confirm it. The center of a neutron star is the only place in the current universe where the conditions may exist, and so we peer at neutron stars from across thousands of light-years, measuring their masses and radii and surface temperatures, trying to read the nature of their deepest interiors from the faintest clues available. The universe hides its most exotic states of matter in the most inaccessible places. The most extraordinary things rest in places we can only approach with mathematics. Even now, as you drift, the deep interior of a neutron star holds a state of matter that has no name agreed upon, in a silence so complete it has never been disturbed. Two merging neutron stars produce a gravitational wave signal that rises in frequency and pitch like a cosmic chirp. As two neutron stars spiral toward each other over millions of years, losing energy slowly to gravitational wave emission, they orbit each other faster and faster. The gravitational waves they produce increase in frequency as the orbital speed increases. What begins as a signal far below any human detectable frequency slowly rises, over millions of years, toward the range that LIGO can detect. In the final seconds before merger, the signal sweeps upward in a rapid crescendo, a chirp that, played as sound, would rise from silence to a high-pitched squeal in the last fractions of a second. The 2017 detection lasted about 100 seconds in LIGO's frequency band, ending in the final plunge. Scientists translated that signal into audio and played it publicly, a brief, rising tone from the other side of the universe, a sound made by two dead stars falling into each other after orbiting for millions of years. The universe composes music. We built instruments small enough to hear it. The universe has always been singing. We are only just learning how to listen. Neutron stars are sometimes found inside globular clusters, where dense stellar environments create unusual binary systems. Globular clusters are ancient, tightly packed spheres of stars, some containing hundreds of thousands of suns in a region just 100 light-years across. In these dense environments, stars interact gravitationally far more often than in the galaxy's open spiral arms. Neutron stars and globular clusters can be captured into binary systems or exchanged between pairs through these close encounters. This process explains why globular clusters contain a disproportionately high number of millisecond pulsars, old neutron stars that have been spun back up by accreting material from a companion. The Terzan 5 globular cluster, for example, contains dozens of known pulsars in a remarkably small volume of space. These ancient clusters, some nearly as old as the universe itself, have been quietly exchanging neutron stars like slow, gravitational trades across billions of years. In the oldest neighborhoods of the galaxy, even the dead stars find new companions. The crust of a neutron star can crack in a starquake, releasing energy equivalent to trillions of nuclear bombs. We have already touched on the crystalline structure of a neutron star's surface, but it is worth dwelling on what happens when that structure breaks. As a neutron star slowly spins down, its shape changes. The centrifugal bulge at the equator gradually shrinks as the rotation slows and the crust must adjust. But the crust is extraordinarily rigid, and it does not adjust smoothly. It holds its shape for a long time, building stress, accumulating strain, and then, suddenly, it snaps. The starquake releases energy in a burst that may last a fraction of a second. The energy involved is enormous, beyond easy comparison, and the effect on the pulsar is measurable. The star suddenly spins faster, then slowly relaxes. The crust has cracked, resettled, and the star continues. What would destroy any human construction is, for a neutron star, a minor adjustment, a quiet settling on a scale of unimaginable force. Even the most rigid things eventually find their way to a new arrangement. Neutron stars possess a kind of natural atomic clock embedded in their pulse timing. The regularity of a pulsar's pulse is not just useful for timekeeping, it also acts as a sensitive probe of the environment the pulsar moves through. As a pulsar travels through space, its signal passes through clouds of gas and plasma. The electrons in that plasma slow the radio waves slightly, with lower frequencies being slowed more than higher ones. By measuring this delay, called dispersion, across a range of frequencies, astronomers can calculate how much ionized gas the signal has passed through. This gives a measure of the distance to the pulsar, since more distant pulsars have passed through more gas. It also reveals the structure of the interstellar medium, the thin, warm plasma that fills the space between the stars. The pulsar's signal is not just a clock. It is a probe, threading through the galaxy and returning information about everything it has passed through on the way to us. Every signal that reaches us has already been shaped by everything it touched along the way. Some neutron stars are cocooned inside their own supernova remnants, still surrounded by the expanding shell of their birth explosion. When a massive star explodes, the outer layers are flung outward at thousands of kilometers per second. This expanding shell of gas and dust, the supernova remnant, glows for tens of thousands of years as it plows through the surrounding interstellar medium. Inside this glowing shell, at the center, the neutron star sits, spinning, radiating, powering the nebula around it. Over time, the remnant expands and fades, until eventually, the neutron star is left exposed in open space, no longer cocooned. The Crab Nebula is still in this cocooned phase, still clearly surrounding its central pulsar. Other pulsars have long since escaped their remnants. The expanding shell has thinned and faded, and the star is now alone. The cocoon, eventually, always disperses. What it protected is left, patient and still, to continue on alone. Everything that shelters us eventually opens. What remains is what was always there. The universe continues while you sleep, and somewhere an ancient shell of light is still expanding outward, from a star that died 100,000 years ago. Neutron stars have been found orbiting massive black holes at the centers of galaxies. At the center of our Milky Way sits Sagittarius A star, a supermassive black hole with roughly 4 million times the mass of our Sun. And near it, orbiting in the intense gravitational environment of the galactic center, astronomers have detected pulsars. These are neutron stars that somehow survived not just their own violent births, but also the turbulent, radiation-drenched environment of the galactic center, where stellar densities are far higher than anywhere else in the galaxy, and gravitational interactions are constant and intense. Detecting pulsars near the galactic center is difficult. The intervening gas scatters their radio signals, but the few that have been found are extraordinary objects for precision physics. Their pulses, timed carefully over years, can probe the space-time geometry near a supermassive black hole with a precision impossible to achieve any other way. A dead star, orbiting a void, serving as a measuring instrument for the deepest physics. The smallest things, placed in the right circumstances, become instruments of the most profound measurements. A neutron star's equatorial circumference, despite its extraordinary density, is smaller than most major cities. The circumference of a typical neutron star, roughly 12 kilometers in radius, is about 75 kilometers. That is roughly the distance from central London to its outermost suburbs, or the distance from one edge of Los Angeles to roughly its center. You could drive that distance in under an hour on an open highway. And yet within that circumference is packed more mass than our Sun, a star so large that its light takes 8 minutes to reach us from 93 million miles away. The entire volume of that mass, compressed into a circle smaller than a metropolitan area. There is something deeply strange about mapping the extraordinary onto the ordinary in this way. The mind cannot truly hold both scales at once. It simply registers something like wonder, quiet, gentle, and without an easy resolution. The most extraordinary things exist at scales the mind reaches toward but cannot quite hold. Some neutron stars are so old they have nearly stopped radiating entirely, dimmed to near invisibility. A neutron star born 1 billion years ago has had a very long time to cool, to slow, to fade. Its surface temperature has dropped from hundreds of millions of degrees to perhaps a few tens of thousands, still hot by human standards, but cold enough that it no longer emits significantly in X-rays or ultraviolet light. Its rotation has slowed from hundreds of revolutions per second to perhaps one per hour or one per day. Its magnetic field has decayed substantially, weakening over geological timescales until the pulsar mechanism can no longer operate. These ancient, dim neutron stars are called retired pulsars, or simply cold neutron stars. We cannot detect most of them. They drift through the galaxy in silence, their surfaces still slightly warm, their interiors still harboring strange matter, their surfaces still crystalline and enormously dense. They are among the most enduring objects in the universe, present, patient, and nearly invisible. Patience, carried long enough, becomes a kind of invisibility. Neutron stars have been used to test Einstein's general relativity with greater precision than any laboratory on Earth. The most stringent tests of general relativity have not come from particle accelerators or precision instruments in quiet labs. They have come from neutron stars. The Hulse-Taylor binary pulsar provided the first indirect confirmation of gravitational wave emission. The double pulsar system, two pulsars orbiting each other, discovered in 2003, has provided even more precise tests of relativistic effects. Scientists have measured the Shapiro delay, the slight slowing of the pulsar signal as it passes through the curved spacetime near its companion, to extraordinary precision. They have measured the rate at which the orbital period decreases due to gravitational wave emission, matching Einstein's prediction to better than 1 part in 1,000. These tests are not just confirmations of a century-old theory. They probe the behavior of gravity in conditions we can never create on Earth, in a regime where general relativity and quantum mechanics both strain against each other without quite touching. The cosmos is the only laboratory large enough to test our deepest theories. Soft gamma repeaters were once thought to be a completely separate class of object from neutron stars. When the first soft gamma repeaters were discovered in the 1970s and 1980s, objects that occasionally released bursts of relatively soft gamma rays, astronomers debated their nature for years. Were they neutron stars? White dwarfs? Some new class of object entirely? The light curves and spectra did not match what was expected from ordinary pulsars. It was not until the 1990s that the theoretical framework for magnetars, neutron stars with extraordinarily powerful magnetic fields, provided the most satisfying explanation. The soft gamma repeaters and the anomalous X-ray pulsars, another puzzling class, were reinterpreted as magnetars. Two previously separate categories collapsed into one. The universe had been showing us the same kind of object from different angles, and we had given it two names. This is how science often works, not in a straight line, but in a slow convergence. Different threads of evidence eventually finding each other in the dark. Knowledge, like light, bends slowly around the shape of what is true. Neutron stars in some binary systems show quasi-periodic oscillations in their X-ray brightness, which may probe the innermost regions of the accretion disk. When material spirals inward toward a neutron star in a binary system, it forms an accretion disk, a flat, swirling structure of hot gas glowing in X-rays. Observations of this X-ray brightness over time show flickering, rapid, semi-regular variations called quasi-periodic oscillations. The frequencies of these oscillations correspond to orbital timescales very close to the neutron star's surface, regions where general relativistic effects are strong and the orbital dynamics are determined by the combination of the star's mass, radius, rotation, and magnetic field. By studying these oscillations, astronomers attempt to map the innermost parts of the disk, regions that are smaller than a city, glowing at millions of degrees, orbiting a dead star at a fraction of the speed of light. This is some of the most extreme physics in the observable universe, visible from Earth only as a faint, rapid flicker in the X-ray count rate. The faintest flickers, studied with enough patience, reveal the most violent places. Some neutron stars absorb their companion star almost entirely, leaving behind only a millisecond pulsar and a tiny, dim remnant called a Black Widow pulsar system. The Black Widow pulsar is named after the spider that consumes its mate, and the analogy is apt, if sobering. In these systems, a rapidly spinning millisecond pulsar irradiates its companion star with intense high-energy radiation and a particle wind, ablating the companion's outer layers, blowing away its mass, bit by bit, over millions of years. The companion star shrinks. Eventually, it may be reduced to a tiny remnant, a few percent of the mass of Jupiter, orbiting the pulsar in a few hours. The pulsar has consumed most of its partner, and in doing so, has maintained its rapid spin. It is both alone and not alone, circling the remnant of what fed it, in a relationship that has lasted billions of years. There is something very still about that orbit. Two objects, one vast in density, and one nearly gone, turning around each other in the faint dark. Quietly, the cosmos moves around you, and some of its partnerships are built on a slow and patient disappearance. Some neutron star mergers may leave behind a hypermassive neutron star before it collapses into a black hole. When two neutron stars merge, the outcome depends on the total mass of the system. If the combined mass exceeds the maximum mass that a neutron star can support, the merged object should collapse into a black hole almost immediately. But if the total mass is close to, but not quite over, that threshold, the merged object may survive for a brief period as a hypermassive neutron star, supported not just by quantum pressure, but by its rapid rotation. It would spin extraordinarily fast, emitting gravitational waves that could in principle be detected, and it would radiate neutrinos and light. After seconds or minutes, the rotation slows enough that the neutron pressure can no longer hold the mass, and the object collapses. This brief, transient phase, a neutron star that exists for seconds, is one of the most sought-after signals in gravitational wave astronomy. A thing that lives for only a moment, at the boundary of what matter is allowed to be. The most fleeting things are sometimes the ones that tell us the most. The maximum mass a neutron star can reach before collapsing into a black hole is called the Tolman-Oppenheimer-Volkoff limit. This limit is the neutron star equivalent of the Chandrasekhar limit for white dwarfs, the maximum mass beyond which quantum pressure can no longer support the object against gravity. For white dwarfs, that limit is about 1.4 solar masses, and it is precisely known. For neutron stars, the equivalent limit depends on the equation of state of ultra-dense matter, the physics of the interior that we do not fully understand. Current best estimates place the TOV limit somewhere between 2 and 3 solar masses, though the uncertainty remains significant. Measurements of neutron star masses in binary systems have helped constrain this range. The heaviest reliably measured neutron star has a mass of about 2.1 solar masses, close to the upper limit. These massive neutron stars press against the boundary of their own existence, resting just below the threshold that would erase them entirely. Everything that exists does so within limits it cannot see and did not choose. Neutron stars were the first objects outside the solar system to have their rotation measured precisely. The discovery of pulsars in 1967 gave astronomers something they had never had before, an extraterrestrial object whose rotation could be measured with the precision of a clock. Before pulsars, measuring the rotation of a distant star was a matter of observing periodic brightness variations, sunspot cycles, binary eclipses, slow oscillations. These were imprecise, messy, difficult to time. A pulsar's radio pulse arrives with such regularity that its period can be measured to the precision of the atomic clocks used to time it. This precision opened entirely new areas of physics, tests of general relativity, measurements of interstellar matter, probes of gravitational waves. It changed what we thought we could measure from the ground. The universe, in providing pulsars, gave us a gift we did not know we needed, a precise, patient, repeating signal from the dark, arriving faithfully, regardless of whether anyone is listening. Some gifts from the universe arrive long before we understand what they are for. Tonight, while you breathe slowly, the first pulsar ever discovered, CP 1919, is still out there, still pulsing, still keeping its patient time in the dark. Neutron stars occasionally emit giant pulses, brief, enormously bright radio flares, many thousands of times brighter than their regular pulses. This phenomenon is not well understood. A small number of pulsars, including the Crab pulsar, occasionally produce individual pulses that are orders of magnitude brighter than their average emission. These giant pulses last for nanoseconds, billionths of a second, but in that brief flash, they can be 10,000 times brighter than the ordinary pulse. They are so bright that the Crab pulsar's giant pulses can be detected with a modest amateur radio telescope, even from Earth. The mechanism behind them is still a subject of debate. Something in the pulsar's magnetosphere, the zone of intense magnetic field and charged particles surrounding the star, occasionally produces a coherent burst of emission, far beyond anything in the normal pulse. It is as if the star, mostly quiet, occasionally speaks very loudly for a fraction of a second, then returns to its patient rhythm without explanation. Even the quietest things, given enough time, occasionally surprise us. Some pulsars have been timed so precisely that astronomers can detect the gravitational influence of a planet orbiting them. In 1992, the first planets discovered outside our solar system were not found around a living star. They were found around a pulsar. Alexander Volstjan and Dale Frail discovered 2 planets, later a third, orbiting the pulsar PSR 12257 plus 12, about 1,000 light-years away, by detecting tiny variations in the arrival time of its radio pulses. The planet's gravity tugged the pulsar slightly as they orbited, causing the pulses to arrive a little early or a little late, depending on the pulsar's position in its small orbit. These were the first confirmed exoplanets, and they orbited a dead star. What those worlds are like is difficult to imagine. They were almost certainly destroyed or stripped by the supernova that created their host star, and what surrounds the pulsar now may have formed afterward from the debris of that explosion. Worlds built from the remains of a catastrophe, orbiting a spinning remnant in the quiet dark. Some worlds come into being not despite a catastrophe, but because of one. Neutron stars can be detected through the way they bend and magnify the light of more distant stars, in a process called gravitational microlensing. A neutron star passing between us and a more distant star acts as a gravitational lens. Its mass bends the light of the background star around it, briefly brightening the distant star's light in a characteristic way. This brightening follows a specific pattern that depends on the mass of the lensing object, allowing astronomers to measure the mass of the neutron star without detecting the neutron star's own light at all. In cases where the lensing object emits no detectable radiation, no X-rays, no radio waves, no visible light, microlensing may be the only way to confirm it is there. Dark neutron stars, invisible by any other means, can still betray their presence by gently bending the light of things behind them. The universe, even in its most invisible objects, leaves a signature in everything it passes. Even the darkest things leave their shape in the light that passes near them. The neutron star in the binary system Hercules X1 pulses in X-rays with a period of 1.24 seconds and shows a complex pattern of longer-term variability. Her X1, as it is commonly called, is one of the best-studied X-ray binaries in the sky. The neutron star orbits a companion star called HZ Hercules every 1.7 days, accreting material and pulsing in X-rays with each rotation. But the system also shows a 35-day cycle of brightening and dimming, thought to be caused by a warped, precessing accretion disk that periodically blocks the X-ray source from view. The system is an intricate, layered dance of physics, rotation, accretion, precession, eclipse, all layered on top of each other and expressed as patterns of varying X-ray brightness. Scientists have studied this system for decades, finding new complexity in data they thought they understood. The universe does not simplify its most interesting objects. It continues to reveal new structure to those who look patiently enough. The more carefully you study a quiet thing, the more layers it reveals. Neutron stars were once thought to be the densest, stable objects possible, but observations now confirm that the maximum mass is higher than originally estimated. Early models of neutron star interiors, developed in the 1930s and refined through the mid-20th century, predicted a maximum mass of about 0.7 solar masses. Later work, incorporating a more complete understanding of the strong nuclear force, revised this upward significantly to around 1.5, then 2, then potentially up to 3 solar masses. The discovery of pulsars with masses near 2 solar masses was, in a quiet way, a revolution. It ruled out many proposed equations of state for ultra-dense matter, all the models that predicted too soft an interior, too compressible, too easily collapsed. The neutron star population is, in this sense, a kind of filter. The universe has been building neutron stars for billions of years, and the ones that still exist are the ones that were stiff enough to survive. The rest became something else. What survives is always, in some sense, a record of everything that did not. There may be strange stars, or quark stars, that are even denser than neutron stars, though none has been confirmed. At densities beyond those of a neutron star, if matter can exist without collapsing into a black hole, it may transition entirely into free quarks. Not neutrons dissolved partially, but a true quark matter core, or even an entire star made of strange quarks. These hypothetical objects are called strange stars, or quark stars. They would be smaller and denser than neutron stars, with different mass-radius relationships that could in principle be distinguished by observation. Several candidate objects have been identified. Neutron stars, whose measured mass and radius seem inconsistent with standard neutron star models, but none has been confirmed as a true quark star. The universe may have built these objects, or it may not have. The evidence remains quiet, ambiguous, inconclusive, and the question stays open, as the best questions do, waiting patiently for better instruments and longer patience. The most important questions are the ones that remain open long after we thought we understood them. Neutron stars rotate at speeds that no human-made object has ever approached. The fastest rotating object ever created in a laboratory setting was a small silica sphere, set spinning by laser light at around 100 billion rotations per minute, roughly 5 billion times faster than a drill bit, and a remarkable achievement of precision physics. But even that extraordinary speed falls far short of a millisecond pulsar. A pulsar rotating at 700 times per second is completing 700 full rotations every second, a rate that, translated to the surface speed of the pulsar, corresponds to roughly 15% of the speed of light. The fastest human-made object, by contrast, moves at a tiny fraction of that. We have never built anything that moves as fast as the surface of the fastest spinning dead star in our galaxy. The universe builds with tolerances we cannot replicate, at speeds we can only observe from very, very far away, in the cool dark between the stars. We have learned to measure what we could never hope to build, and that is its own kind of wisdom. Neutron stars are the only objects in the universe where all 4 fundamental forces of nature are simultaneously important. In everyday life, we live mostly under the influence of gravity and electromagnetism. The strong and weak nuclear forces operate only at subatomic scales. They hold nuclei together and govern radioactive decay, but they do not reach the scale of our everyday experience. In a neutron star, all 4 forces are at work, and all 4 matter for the star's structure and behavior. Gravity determines the overall collapse. The strong nuclear force governs how the neutrons resist that collapse. The weak nuclear force governs the reactions that create neutrons from protons and electrons, and that produce the neutrinos that carry away heat. Electromagnetism governs the magnetic field that shapes the pulsar beam and drives the jets. Nowhere else in the universe, at least no place we can study, do all four forces meet at such extremity. A neutron star is, in a quiet sense, the most complete physics laboratory in existence. In the most extreme places, everything that holds the universe together must work at once. The universe is patient, so are we. The light that left a neutron star before our solar system existed is still traveling through the dark. Our sun formed roughly 4.5 billion years ago from a collapsing cloud of gas and dust. Some neutron stars are far older than that, born in the first billion years of the universe, when the earliest massive stars burned through their fuel and collapsed. The light those stars emitted in their deaths, the radiation their neutron star remnants have been sending outward ever since, has been traveling through space for longer than our planet has existed. There is something very still about that image, a signal older than the Earth, moving through the dark at the speed of light, carrying information about a place and time so remote that no human concept of distance or duration can fully hold it. We live inside a universe far older than our own story. The light that surrounds us on all sides is ancient in ways that dissolve the edges of what we call time. Even now, as you drift, light older than the Earth moves through the room you are resting in. Some neutron stars are moving through the galaxy at thousands of kilometers per second. When a massive star explodes asymmetrically, when the supernova is not perfectly even on all sides, the neutron star can receive a kick, a natal kick, astronomers call it. The uneven blast pushes the neutron star in one direction, like a rocket fired from the center of the explosion. Some neutron stars receive kicks of hundreds of kilometers per second. A few have been found moving at over 1,000 kilometers per second, fast enough to eventually escape the Milky Way entirely, to cross intergalactic space and drift alone between the galaxies forever. These are called runaway pulsars. They were born inside the galaxy, among the stars, surrounded by gas and light. And then they were flung outward, alone, with no companion, no nebula, no remaining connection to anything, crossing the galaxy at a speed that would carry them from one side of the Milky Way to the other in 100 million years. Patient, drifting, alone. Some things in the universe are set moving at the moment of their birth and never stop. Neutron star surfaces, despite their extraordinary temperatures, are dark to human eyes because their light peaks in the X-ray band. We associate heat with visible light. A fire glows orange and yellow. A tungsten filament glows white. A surface temperature of millions of degrees, however, pushes the peak of the emission curve far past visible light, deep into the X-ray portion of the electromagnetic spectrum. A young neutron star, if you could somehow see it with unprotected human eyes from a safe distance, would appear dark. Not black, exactly. It would emit some faint, ultraviolet radiation at its edges, but not the blazing visible light we might expect from something so hot. Its X-ray brilliance is invisible to us without instruments. In a sense, the most extreme heat in our cosmic neighborhood is also, to our unaided eyes, the most invisible. The universe has many registers, and our vision covers only a very narrow slice of what is actually there. What burns most brightly is not always what we can see. Some neutron stars have a slight wobble in their pulse timing that reveals a tiny deformation in their shape, a mountain no taller than a few centimeters. The surfaces of neutron stars are not perfectly smooth. Even the extraordinary rigidity of nuclear pasta and crystalline crust cannot maintain perfect spherical symmetry under the stresses of rotation, accretion, and magnetic field. A neutron star may have a surface deviation, a bump or mountain, just a few centimeters in height. That is the scale of a small rock or a shoebox. And yet, because of the extreme gravity, even that small asymmetry represents an enormous concentration of mass, offset from the rotation axis. This asymmetry would cause the star to emit continuous gravitational waves as it spins, a steady, low hum in the fabric of spacetime, quiet and persistent, distinct from the sharp chirps of mergers. These continuous gravitational waves have not yet been detected, but searches are ongoing. The universe may be humming to us, very softly, through the shape of a mountain no taller than your knee. The smallest imperfection, in the right place, becomes a song. Neutron stars have been found in the most ancient globular clusters, meaning some neutron stars are nearly as old as the universe itself. The universe is approximately 13.8 billion years old. The oldest globular clusters, tight, spherical collections of hundreds of thousands of stars, formed within the first billion years, when the universe was still young and densely packed. The most massive stars in those clusters burned through their fuel and collapsed long ago, leaving neutron stars behind. Some of those neutron stars have been spinning for 12 or 13 billion years. They have been turning since before our sun existed, before our galaxy had its current shape, before most of the stars visible in tonight's sky had formed. They carry, in their slow spin and cooling surfaces, a memory of a universe that looked very different, hotter, denser, more turbulent. They are among the oldest objects we can study, resting in the dark, turning, for almost the entire history of time. Some things have been patient, since before patience had a name. Neutron stars radiate in gamma rays, through a mechanism distinct from pulsars, called gamma-ray pulsars. They were only confirmed when the Fermi telescope launched in 2008. For decades, astronomers knew that some pulsars emitted in radio waves and some in X-rays, but the existence of clean gamma-ray pulsars, objects beaming gamma rays without corresponding radio emission, was uncertain. The Fermi Gamma-Ray Space Telescope, launched in June 2008, changed that. It discovered hundreds of gamma-ray pulsars, including many that produce no detectable radio emission at all. These radio-quiet gamma-ray pulsars are invisible to the large radio telescope arrays that found most known pulsars. They exist in a separate observational regime, revealed only by Fermi's wide-field gamma-ray vision. The galaxy contains an entire population of pulsars that older instruments could not see. This is a quiet reminder that what we know about the universe is always shaped by the instruments we happen to have built so far. The sky changes as our ability to read it improves. The universe shows us more of itself each time we build something sensitive enough to listen. The nearest known neutron star to Earth is RxJ1856-3754, located about 400 light-years away. 400 light-years is, in cosmic terms, very close. It is close enough that this neutron star, a member of the Magnificent Seven, slowly cooling in the dark, has a measurable parallax, meaning astronomers can track its tiny shift against the background stars as the Earth moves around the Sun, and use that shift to calculate its distance directly. It drifts through space at a modest speed, cooling very slowly, emitting a faint glow in soft X-rays. It poses no danger to us at this distance. It is simply there, a dense, dim remnant, the quietest kind of neighbor, tracing its slow arc through the galaxy, with no companion, no pulse beam sweeping our way, no drama of any kind. Just a warm, dense object in the dark, several thousand trillion kilometers away, going about the slow business of cooling. The nearest extraordinary thing is still so far away that its light takes 4 centuries to reach us. Neutron stars can transfer angular momentum to a companion star through their magnetic field, slowing their own spin. In some binary systems, the relationship between a neutron star and its companion is not simply accretion. The neutron star's rotating magnetic field can interact with the companion's atmosphere or the accretion disk in ways that transfer angular momentum, the physics of rotation, from the neutron star outward, slowing the neutron star's spin while affecting the companion. This regime, called the propeller effect, occurs when the neutron star is spinning fast enough that the centrifugal force at the magnetosphere boundary exceeds the infall of material, flinging the incoming gas outward rather than letting it fall in. The neutron star acts as a propeller, pushing material away rather than drawing it in. In this state, the star can spin down rapidly, far faster than it would through pure electromagnetic emission alone. These transitions between accretion and propeller states are observable as sudden changes in X-ray brightness. The neutron star, in a sense, decides what it will and will not accept. There are states in which even the densest things push back against what approaches them. The thermal emission from a cooling neutron star follows a spectrum that is distorted by the extreme gravity at its surface. A perfect thermal emitter, a blackbody, produces light distributed in a specific pattern across wavelengths that depends only on its temperature. Neutron stars are close to blackbody emitters, but not perfect ones, and the spectrum that emerges from the surface is further distorted by the extreme gravity and magnetic field. The light must climb out of the deep gravitational well, losing energy as it does. The gravitational redshift shifts the spectrum to lower energies. The strong magnetic field splits and polarizes the emission in ways that depend on the orientation of the surface relative to the field lines. Studying these distortions allows physicists to disentangle the surface temperature, the magnetic field strength, the gravitational redshift, and therefore the mass-to-radius ratio of the star. Each photon that escapes a neutron star carries a tiny encoded message about the conditions it left behind. The universe encrypts its secrets in the light it allows to leave. Every photon that escapes carries the memory of the place it came from. Neutron stars are the most precise natural timepieces known to exist in the universe. We have already touched on the clock-like regularity of millisecond pulsars. But it is worth dwelling on what precision means in this context. The best atomic clocks on Earth keep time to within 1 second in about 300 million years. Millisecond pulsars, over timescales of years, can approach or exceed this level of stability. Their spin-down rates are so gradual and so predictable that astronomers can model their behavior over decades, predict the arrival time of the next pulse weeks in advance, and detect deviations smaller than a microsecond. This precision has practical implications. Pulsar timing arrays, if they succeed in detecting the gravitational wave background, will use these natural clocks as the detectors. The universe has built timekeeping devices that rival or exceed our best technology, from the wreckage of dying stars, without any design, without any intention, simply by following the slow, patient logic of physics. The universe builds its most precise instruments from its most violent events, and does not rush them. As you rest tonight, a millisecond pulsar somewhere in the Milky Way has completed more than 1 trillion rotations since the Earth formed, keeping time across the entire span of our planet's existence. The study of neutron stars has changed our understanding of nuclear physics in ways that cannot be replicated in any laboratory. The densities and pressures inside a neutron star are beyond the reach of any particle accelerator currently built or planned. The Large Hadron Collider at CERN can briefly create quark-gluon plasma in small regions through particle collisions, but these regions are fantastically small and fantastically brief. A neutron star maintains those conditions across a volume kilometers in diameter, continuously, for billions of years. Observations of neutron star masses, radii, temperatures, and cooling rates constrain the behavior of matter at nuclear and subnuclear densities in ways that complement and extend what laboratory physics can tell us. The two approaches, theoretical physics, laboratory experiment, and astrophysical observation, form a three-way conversation about the nature of matter at its most extreme. Neutron stars are not just objects, they are experiments that the universe has been running for billions of years, patiently, without our input. The universe has been doing the experiment longer than we have been asking the question. Neutron stars occasionally emit fast radio bursts, brief, enormously energetic pulses of radio waves lasting milliseconds. Fast radio bursts were first detected in archival data in 2007. Bright, brief flashes of radio waves, lasting a few milliseconds, arriving from cosmological distances, carrying in their dispersion measures the signature of having passed through billions of light-years of intergalactic plasma. Their origin was debated for over a decade. In 2020, a fast radio burst was detected from a magnetar within our own galaxy, SGR 1935 plus 254, and simultaneously detected by two different observatories, confirming for the first time that at least some fast radio bursts come from magnetars. The mechanism likely involves the sudden catastrophic reconnection of magnetic field lines, a process releasing enormous energy in a fraction of a second. The universe occasionally snaps, very briefly, very brightly, from the surface of a dead star, and the snap reaches us, across billions of light-years, as a brief whisper of radio noise that lasts less time than it takes to breathe in. The briefest signals sometimes carry the longest journey. Neutron stars can be used to measure the expansion rate of the universe when they merge. The Hubble constant, the rate at which the universe is expanding, has been measured in two primary ways, and they disagree. Measurements using the cosmic microwave background and measurements using local distance indicators give results that are tantalizingly different, a discrepancy physicists call the Hubble tension. Neutron star mergers offer a third, independent method. When two neutron stars merge, the gravitational wave signal encodes information about the absolute distance to the merger, independent of any cosmic distance ladder. Combined with the light from the kilonova, which gives the recession velocity, the merger event gives a direct measurement of the Hubble constant. The 2017 detection gave a first estimate consistent with both methods, but not yet precise enough to resolve the tension. Future detections, dozens or hundreds of them, may finally resolve the disagreement. Dead stars, falling together, may tell us how fast the universe is running from itself. Even in their ending, some things help us understand the shape of the whole. A neutron star's interior may be divided into distinct layers, each with its own exotic physics, like geological strata on a cosmic scale. From the outside in, a thin outer atmosphere of hydrogen or helium, a photosphere, an outer crust of iron nuclei in a crystal lattice, an inner crust of neutron-rich nuclei embedded in a neutron superfluid, a liquid outer core of mostly neutrons with some protons and electrons, and then, possibly, a deep inner core of quark matter or color superconducting strange matter. Each of these layers transitions into the next, across distances of perhaps a few hundred meters, at densities that increase by orders of magnitude from one boundary to the next. The entire structure is smaller than a large city. It contains within it, stacked in a few kilometers, the range from ordinary nuclear matter to conditions that may not have existed freely since the first microseconds after the Big Bang. A small object, carrying the history of matter's most extreme possibilities, drifting in the patient dark. In a very small space, the universe arranges its most extreme possibilities in quiet layers. Some neutron stars pulse not in radio or X-rays, but in visible light. A handful have been detected optically with large ground-based telescopes. We tend to think of neutron stars as radio or X-ray objects. But the Crab pulsar, one of the most studied pulsars in the sky, also pulses in visible light, 30 times per second, a rapid flicker that is invisible to the naked eye, but detectable with a fast photometer on a large telescope. A few others have also shown optical pulsations. These are faint, extraordinarily faint, but they are there. The optical emission from a pulsar is thought to come from the outer regions of the magnetosphere, where charged particles radiate across a broad range of frequencies. Detecting these optical pulses requires large telescopes, fast electronics, and very dark skies. But it is a remarkable thing to consider that there are dead stars in the sky that are literally flickering in the same band of light that your eyes evolved to see, 30 times every second, carrying their quiet signal across thousands of light years to fall, invisibly, into the night. Even now, light from a dead star is falling on you, too faint to feel and too fast to see. The cooling of a neutron star is thought to involve a process called the direct Urca process, named after a nightclub in Rio de Janeiro. The name has an odd and charming origin. The direct Urca process is a sequence of reactions in which a neutron decays into a proton, an electron, and an antineutrino, after which the proton captures an electron and becomes a neutron again, releasing another neutrino. These reactions carry away enormous amounts of energy in the form of neutrinos, causing the neutron star to cool very rapidly. A Russian physicist, comparing this rapid energy loss to the rapid loss of money at a casino, named the process after the Casino da Urca in Rio de Janeiro, which was at the time the most efficient place he could think of for losing money quickly. The name stuck, and so, embedded in the technical literature of neutron star astrophysics, is a quiet reference to a casino in Brazil. Even in the most rarefied corners of physics, humanity finds a way to leave a personal note. The universe is immense, and yet the people who study it are always, quietly, still human. Neutron stars produce neutrinos in such enormous quantities during their birth that a single supernova can briefly outshine the entire visible universe in neutrino luminosity. The neutrino is one of the most elusive particles in nature. It has almost no mass, carries no charge, and interacts with ordinary matter so weakly that a neutrino can travel through a light year of solid lead with only a 50% chance of interacting. And yet, in the first seconds of a neutron star's birth, the star emits more energy in neutrinos than our sun will emit in all forms of radiation across its entire 10 billion year life. In those few seconds, the neutrino luminosity of the collapsing star exceeds the combined visible light output of all the stars in the observable universe. In 1987, a supernova occurred in the Large Magellanic Cloud, a nearby satellite galaxy, and 24 neutrinos were detected by underground neutrino observatories around the world. 24 particles, from a flood of 10 to the 58th, detected by instruments the size of buildings. The universe passed through us that day, and we noticed 24 of its footsteps. The universe moves through us constantly, and we catch only the faintest trace of its passing. The light echo from a supernova that created a neutron star can still be visible centuries after the explosion. When a star explodes, the flash of light from the explosion travels outward in all directions. Some of that light travels directly toward us, but some travels outward in other directions, strikes surrounding clouds of dust and gas, and is reflected toward us, arriving later because it has taken a longer path. This is called a light echo, a slowly expanding ring of reflected supernova light, visible years or decades, or even centuries after the original explosion. In some cases, light echoes have been detected around known supernova remnants, where the original explosion occurred hundreds of years ago. The light we are seeing in those echoes left the explosion at the same moment as the light that arrived centuries earlier. It simply took a longer route. Looking at a light echo is looking at the past, at a different angle. The universe keeps its old light for a very long time, in the reflective surfaces of quiet clouds. Even the most ancient flashes leave traces, reflecting slowly in the patient dark. Neutron stars are thought to be the source of some cosmic rays, enderos, particles that arrive at Earth with energies far beyond what any accelerator has produced. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that arrive at Earth from space, moving at very nearly the speed of light. Their origins are debated, but neutron stars in binary systems and pulsar wind nebulae are strong candidates for the acceleration of at least some of them. The spinning magnetic field of a pulsar can act as an enormous particle accelerator, flinging electrons and positrons outward in a pulsar wind at extreme energies. These particles interact with the surrounding gas, producing the glowing pulsar wind nebulae, visible around many young pulsars. Some may escape the nebula entirely and travel through the galaxy, arriving eventually at Earth as cosmic rays. If so, some of the high-energy particles that strike our upper atmosphere every day, creating the faint background of cosmic ray secondaries that passes through your body as you lie here, may have been accelerated by a spinning dead star. Even now, particles flung by a dead star are passing through you, ancient and patient and undetected. A neutron star's magnetic pole and its rotational pole are typically misaligned, which is what creates the pulsar lighthouse effect. On Earth, the geographic poles and the magnetic poles are not perfectly aligned. The magnetic north pole drifts over time and currently sits several hundred kilometers from the geographic north pole. On a neutron star, this misalignment is both common and essential to what makes a pulsar visible. The beam of radiation emerges from the magnetic poles, where the field lines converge and particles are accelerated. Because the magnetic poles are tilted relative to the spin axis, the beam sweeps around like a lighthouse with each rotation. If the beam never swept across Earth's direction, we would never know the pulsar was there. Most neutron stars are likely invisible to us, not because they are not pulsing, but simply because their beam does not happen to sweep our way. We see only the ones that are aimed at us, and even those, only at the moments when their beam swings through our line of sight, once per rotation, like a slow wave from the dark. Most of the signals in the universe are aimed somewhere else entirely, and we will never receive them. Some neutron stars are embedded in the remnants of their supernova for tens of thousands of years. The Crab Nebula is roughly 1,000 years old and still clearly surrounding its pulsar. The Cassiopeia A supernova remnant, about 300 years old as seen from Earth, still surrounds its central neutron star in a glowing, tangled shell of elements forged in the explosion: silicon, sulfur, calcium, iron, argon. The neutron star at the center of Cassiopeia A is one of the best-studied young neutron stars in the sky, its surface temperature dropping measurably over the years of observation, its cooling curve fitting models of neutron star interiors in ways that constrain the deep physics. It is surrounded by the very material that once made up the star that became it, a shell of past life circling the dense remnant of what that life left behind. The star, in exploding, scattered itself across the sky. What remained at the center has been watched, quietly, for 300 years. What a thing leaves behind often tells us more about it than the thing itself ever could. A neutron star's gravitational field is strong enough to focus its own back hemisphere radiation toward observers in certain directions. This is called gravitational lensing of the neutron star's own emission, self-lensing. Normally, the radiation from the back hemisphere of a star is blocked by the star itself. You cannot see the side facing away from you. But near a neutron star, the curvature of space-time is so extreme that light from the back hemisphere, rather than traveling away from us in a straight line, curves around the star and toward us. The result is that a distant observer sees more of the neutron star's surface than half. In some models, as much as 80 to 90% of the total surface contributes to the observed emission. This means that when we observe the pulsing of a neutron star's hotspot as it rotates, the pulse modulation is smaller than it would be without this lensing. The hidden side is always partially visible. The star cannot fully hide any part of itself. Its own gravity reveals it. Some things cannot conceal themselves because their very nature bends the space around them toward transparency. The universe continues while you sleep, and right now, a neutron star, 1,000 light-years away, is cooling by a fraction of a degree, its crust settling by the width of an atom, its pulse arriving faithfully at the edge of our solar system where no instrument waits to receive it. The gravitational binding energy released when a neutron star forms is roughly 10 times the sun's entire energy output over its lifetime. When the core of a massive star collapses to form a neutron star, the energy released in gravitational binding, the energy of all that matter falling inward together, is roughly 3 times 10 to the power of 46 joules. Our Sun will emit, across its entire 10 billion year life, roughly 10 to the power of 44 joules. The collapse releases, in less than a second, approximately 10 times that amount. 99% of it leaves as neutrinos. 1% drives the supernova explosion. A fraction of a fraction goes into the kinetic energy of the neutron star's kick. And what remains, the neutron star itself, carries only a tiny sliver of the original energy, mostly as heat and rotation. The universe, in the birth of a neutron star, performs one of the most energetic events in its history, and hides almost all of that energy in particles that pass through everything without stopping. The most powerful events in the cosmos do their work invisibly and move on without a trace. A neutron star's rotation can be maintained for billions of years by accreting only a small amount of material. Millisecond pulsars are old neutron stars that have been spun back up to high rotation rates by accreting material from a companion star. The amount of material required to spin a neutron star up to hundreds of rotations per second is surprisingly small, perhaps a few hundredths of a solar mass, accumulated over hundreds of millions of years. The companion star, slowly losing mass through a stellar wind or Roche lobe overflow, provides this material drop by drop across unimaginable timescales. Each small parcel of infalling matter carries angular momentum, and that momentum is deposited into the spin of the neutron star. Over 100 million years, these tiny deposits accumulate into the extraordinary rotation of a millisecond pulsar. The patience of the process is almost incomprehensible. 100 million years of slow, steady accumulation, each moment indistinguishable from the last, building toward something that will then spin faithfully for another several billion years. The most enduring things are often built by the slowest processes. Some neutron stars have been found to switch between pulsar and accreting states on timescales of years or even weeks. These objects, called transitional millisecond pulsars, move back and forth between two very different modes of behavior. When material flows in from a companion star at a sufficient rate, the infalling gas suppresses the pulsar mechanism, the radio emission stops, and the system glows in X-rays as an accreting system. When the accretion rate drops, the radio pulsar mechanism switches back on, and the system once again sends its regular pulse outward. In one object, designated PSR J1023+0038, astronomers have observed this transition happening multiple times. The system switches modes, back and forth, on timescales short enough to study in a single astronomer's career. It is a rare thing, an object caught in the act of becoming what it will eventually be, permanently. A system in transition, neither fully one thing nor the other, oscillating between two states with a patience that spans years. Some things exist most fully in the space between what they were and what they are becoming. Neutron stars may eventually evaporate their companion stars entirely, leaving isolated millisecond pulsars behind. The Black Widow and Redback pulsar systems, binary systems where the pulsar is actively ablating its companion with radiation and a particle wind, are thought to be the intermediate stage in a process that eventually leaves the pulsar alone. As the companion loses mass, it shrinks. Its orbit changes. The irradiation from the pulsar continues, stripping away more and more material. Eventually, the companion may be reduced to a planetary mass object, a few percent of Jupiter's mass, or may evaporate entirely, leaving only the isolated millisecond pulsar behind. The isolated millisecond pulsars that we observe today, spinning rapidly with no companion, may all be the survivors of this process. They consumed what kept them spinning, and then continued alone. Dense, fast, old, and very quiet, drifting through the galaxy without company, carrying a rotation rate that testifies to a relationship that no longer exists. What something consumed, long ago, is written in how fast it still turns. Neutron stars have been detected at the centers of some of the most ancient supernova remnants still visible in the galaxy. The oldest supernova remnants visible to us have expanded so far that they have thinned to near invisibility, vast, faint halos of warm gas, detectable only in the radio and in deep X-ray surveys. At the centers of some of these ancient remnants, pulsar searches have found faint, slowly spinning neutron stars still in residence. These pulsars are old. Their rotation has slowed considerably. Their emission has faded. But they are still there, still turning, still sending their signal outward into space that was once filled with the glowing debris of their birth. The remnant has dispersed into the surrounding interstellar medium. The star persists. Of the two, the bright explosion and the quiet remnant, it is the quiet one that endures. The light faded long ago. The dense thing at the center continues. Quietly, the cosmos moves around you, and of all the things that an explosion leaves behind, the stillest is always the last to go. The equation of state of neutron star matter will likely be fully constrained within the next decade of observations. The NICER telescope on the International Space Station is continuing to refine measurements of neutron star masses and radii. The next generation of gravitational wave detectors, including upgraded versions of LIGO and the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will detect dozens to hundreds of neutron star mergers, each one adding constraints on the equation of state. Future X-ray observatories will study the thermal emission from neutron star surfaces with greater precision than ever before. The combination of these instruments, over the coming decade, should narrow the uncertainty enough to distinguish between competing models of the deep interior, to determine whether the core contains only neutrons, or hyperons, or quark matter. We are, in a historical sense, very close to understanding what the densest matter in the universe is made of. An answer that took almost a century to approach is growing slowly nearer, fact by fact, pulse by pulse, in the patient dark. The answers we have been building toward for a century are still arriving, one observation at a time. Some neutron stars show a phenomenon called mode switching, where the pulse profile abruptly changes shape for hours or years, then changes back. A pulsar's pulse profile, the precise shape of its radio emission as a function of rotation phase, is usually extraordinarily stable. It can be used as a fingerprint. But in a small number of pulsars, this profile spontaneously switches between two or more distinct shapes. For hours, the pulsar emits in one mode. Then, without any apparent trigger, it switches to a different emission pattern. Different relative brightnesses of pulse components, different widths. And then, later, it switches back. These transitions happen on timescales of seconds to years, with no obvious cause. The magnetosphere of the pulsar, the plasma-filled region around the star, is somehow reorganizing itself into a different configuration, and then reorganizing back. It is a reminder that even the most regular objects in the universe have an inner life that we do not fully understand. Even the most faithful clock, it turns out, occasionally does something different for a while. Even the most patient things carry within them a quiet capacity for change. Neutron stars are the remnants of stars that were, for millions of years, among the brightest objects in their neighborhood of the galaxy. A star massive enough to eventually become a neutron star, perhaps 15 or 20 times the mass of our Sun, is extraordinarily luminous while it lives. It burns through its hydrogen fuel not in 10 billion years, like our Sun, but in 10 million, 1,000 times faster. For those 10 million years, it blazes at perhaps 100,000 times the luminosity of the Sun, outshining everything around it, ionizing the gas nearby into glowing nebulae, driving stellar winds that reshape the surrounding interstellar medium. And then it ends. In a second, it collapses, and the extraordinary, blazing thing becomes a cold, dense, quiet remnant, 10 miles across, cooling slowly in the dark. The contrast is almost too large to hold. 100,000 suns of light, reduced to a city-sized ball of neutrons. The universe contains both things in the same object, separated by a fraction of a second. The brightest things leave behind the stillest remains. Neutron stars provide the best evidence we have that the universe obeys the same physics in all its corners. Every test we have applied to neutron stars, the timing of pulsar signals, the masses and radii of neutron stars, the gravitational wave signals from mergers, the energy spectrum of their surface emission, has returned results consistent with the laws of physics as we understand them. General relativity, quantum mechanics, nuclear physics, electromagnetism, all tested simultaneously in an extreme environment on the far side of the galaxy, and all confirmed. The same equations that were written down in terrestrial laboratories, in quiet rooms, by people who could not have imagined the conditions of a neutron star's interior, describe that interior with extraordinary precision across thousands of light years. The universe, in all its corners, in all its extremes, obeys the same quiet rules. The same rules that hold you gently in your bed, that keep your atoms together, that govern the slow chemistry of your breathing. Those rules, unchanged, govern the most violent and dense objects we have ever found. The laws that hold you together tonight are the same laws that hold the farthest star in its slow turning. Slowly, gradually, every neutron star in the universe will cool to the temperature of the space around it, growing dark and still. The universe is approximately 13.8 billion years old, and its most ancient neutron stars are already billions of years along in their cooling. But the endpoint, a neutron star cooled to the temperature of the cosmic background radiation, just a few degrees above absolute zero, is still far in the future. It will take perhaps 10 to the 20th years, a number so large it has no intuitive meaning. On timescales like that, the galaxy itself will have changed beyond recognition. The stars will have burned out. The stellar populations will have shifted to dim, long-lived red dwarfs, and then to white dwarfs, and then to black dwarfs, objects that theory predicts, but that do not yet exist anywhere in the universe. It has not been old enough. In that vast future, neutron stars will still be cooling, patient, still, growing imperceptibly colder, degree by degree, across timescales that the universe itself has not yet lived. In the longest story the universe will ever tell, even the densest things are still waiting for their ending. Some neutron stars have been studied for longer than some scientists have been alive. The Crab pulsar has been studied since its discovery in 1968, the Vela pulsar since 1968, PSR B 1919 plus 21, the first pulsar discovered, has been monitored for nearly 60 years. There are scientists who have dedicated their entire careers to a single pulsar, spending decades refining timing models, measuring spin-down rates, searching for glitches, building a record of pulse arrival times that stretches back further than their children have been alive. These are acts of extraordinary patience, human lifetimes devoted to monitoring an object that does not know it is being monitored, that would spin on regardless, that has been spinning since long before any human civilization existed. The relationship between an astronomer and their pulsar has a quality that is hard to name. Something like companionship, across an impossible distance, between a life that is brief and a thing that will outlast everything we have ever built. Some forms of devotion are offered to things that will never know they were loved. The universe, after all its complexity, after all its extremes, returns always to the same quiet things. Stars are born from gas and dust. They burn, they end. What remains endures. Matter cycles through forms we cannot fully imagine, from the hot plasma of stars to the crystal lattice of neutron star crusts, from the strange fluid of a superfluid core to the free quarks that may exist in the deepest interiors. Energy moves from one form to another, from nuclear binding energy to neutrinos, to X-rays, to the slow warmth of cooling. Nothing is created in these transformations. Nothing is lost, only changed, only moved. And through all of it, the slow turning continues, the universe rotating at every scale, from subatomic spin to galactic arms, a nested series of circles inside circles, all of them patient, all of them ancient, all of them following rules they did not choose and could not break. You are part of this. Right now, resting, breathing slowly, you are part of the turning. You are still, and yet you are moving, carried by a planet that has been circling a star for 4.5 billion years, in a galaxy that has been turning for 10 billion more. Every atom of iron in your blood was forged in the core of a massive star that ended its life in a supernova, long before our solar system existed. Not iron from one star, iron from many stars, different generations, different masses, different corners of the galaxy, each of them burning through its fuel, reaching the end, collapsing, scattering. The iron from those explosions drifted through space, slowly, mixed with hydrogen and helium and carbon and oxygen, and eventually fell into the cloud of gas that became our solar system. It settled into the early Earth. It was incorporated into the first oceans. It entered the chemistry of early life. Over billions of years of evolution, it found its way into the hemoglobin of your red blood cells, where it holds oxygen and carries it through your body with every heartbeat. The iron pumped through your heart right now has already lived through the death of stars. It has already survived a supernova. It is ancient beyond any measure your life provides. And it rests inside you, warm and quiet, as you breathe. You carry the galaxy in your blood, and it has been patient far longer than you have existed. Now let the science fall away. Let the numbers dissolve. Let what remains be only this. You are a small, warm thing in a vast, cool universe, and the universe is not indifferent to you. It is simply immeasurably large. The same forces that shaped neutron stars shaped you. The same physics that allows a dead star to spin for billions of years in the dark allows your neurons to fire, your lungs to expand, your heart to move in its slow, faithful rhythm. You are not separate from any of this. You are made of it. Every breath you take connects you to a chain of events that stretches back to the first second of the universe, to the first quarks, the first nuclei, the first stars, their deaths, their remnants, the slow mixing of elements across billions of years, and finally, here, the particular arrangement of atoms that is you, resting in the dark, listening to the slow story of the cosmos. Let your body grow heavier. Let the night grow quiet around you. There is nothing left to hold on to tonight. The neutron stars are still turning. They do not need your attention. They have been turning since before you were born, and they will turn long after everything you have ever known is gone. And that is not a sad thought. It is a freeing one. In the vast patience of the universe, your rest tonight is not insignificant. It is part of the same slow rhythm. Your sleep is a small, quiet thing in the middle of something unimaginably large, and that is exactly what it should be. You are allowed to be small. You are allowed to be still. You are allowed to let the turning continue without you, for a few hours, while you sink into the dark and rest. The iron in your blood was forged in the heart of a dying star. You are old in ways you cannot feel, and you belong here, in this moment, in this quiet, in this dark. Let your thoughts slow now. Let them drift like light across the long dark between the stars, not going anywhere in particular, not needing to arrive, just moving, slowly, through the cool and ancient space between one thought and the next. You do not need to hold anything tonight. The cosmos will hold it for you. It has held much larger things than this, for much longer than this, without effort and without complaint. It is very good at holding things, and you are very good when you allow yourself to be, at letting go. Breathe in, slowly. Breathe out. The stars are still there, and so are you. and the distance between you is both infinite and, in some deep sense, that the science points toward without quite reaching. Not a separation at all. You are resting now. The galaxy turns. The pulsars pulse. The magnetars cool in the far dark. The light that left a star 1 billion years ago is still moving through the black, faithfully, without hurry. There is nothing else tonight but this. A quiet room, a slow breath, the ancient dark pressing gently in from all sides, and the universe, patient, immense, and very, very old, holding everything in its slow and wordless embrace. I hope you